Hello, and welcome to 123 AP Physics with Zach Speaks the Science Geek. This week, we're learning all about circles. Basically, for everything we've learned so far, there's an analog for circles. For kinematics, there's rotational kinematics. For dynamics, there's rotational dynamics. For work and energy, there's work and energy for circles. There's an analog for everything. So this is going to be a lot of content, but unfortunately not many problems this week. So if you want more problems, just Google some AP Physics dynamics problems, or rotational kinematics problems, or rotational work and energy. So let's get started. Okay, so the first thing is centripetal force, because as we know from forces and vectors, right, Newton's law says that if there's no force acting on an object, it's going to keep traveling in the same path. And the same path is always going to be a vector. It's always going to be a line, right? So how do things keep moving in a circle? Well, a force called the centripetal force, which could be any number of forces, keeps it in a circle. So like, if you got something revolving on a desk, and if you got something revolving on a string, right, and you've got it so that you're spinning the string and it's making circles, the tension of the string on the weight on the end is the centripetal force. The tension is the centripetal force, but it's also still tension. And so the formula for it is the force is equal to the mass of the object times by the velocity of the object squared divided by the radius of the circle. And the acceleration, then you cancel out mass on both sides, and it's just velocity squared over the radius. So let's get started with kinematics. So it's the same as regular kinematics, except there's different symbols now. So we have omega, which is angular velocity, and it's also equal to the velocity over the radius. So the velocity of the object divided by the radius of the circle it's traveling in will tell you the angular velocity. You have alpha, which is the angular acceleration, so the analog for just regular acceleration, and that's a over r. You have theta, which is angular distance, the analog for like x from y, and you still have time, and you have omega naught and omega final as usual. So you just replace the regular kinematics formulas with the new corresponding symbol to create the rotational kinematics formulas. So like you'd have omega equals omega naught plus at plus alpha t. Yeah. So dynamics. Okay, so you have torque, right? Torque is the force in circles, and it's equal to the actual force times by the radius of the circle or the object, the distance from the center of mass usually for the object, or the point of rotation for the object, to where the force is applied times the sine of the angle between them. That's a cross product. And so the net torque is equal to I alpha. Torque is a three-dimensional vector because it's a cross product, so it could be either clockwise or counterclockwise. You can use the right hand rule. So like if you take your right hand and you wrap it in the direction of motion, the way your thumb points out would tell you if it's clockwise or counterclockwise. Or you could imagine like the net torque as one vector, and you put it at the distance, and you see if it's pointing up, then it would be, if it's pointing upwards, if it's pointing away from the center of mass, or away or towards the center of mass, depending on where it's located, that'd tell you if it's clockwise or counterclockwise. So r is distance from the pivot point, and if it's not rotating, you can place a pivot point anywhere because there's no net torque. And so that's used in some problems where you don't know all the forces, like a block might be strapped to a wall or something, and you don't know the normal force, you don't know the torque that's generating, but by placing a pivot point where it's connected, you can just cross out because there's no radius, there's no distance from the pivot point. or the degree between the two is 180 or 0, and that would also cancel it out. And so I is the object's resistance to motion, or the moment of inertia. And so that it varies from object to object. The usual form is some coefficient like 1/3, 2/3, 1/6 times by the radius, times by the mass of the object, times by the radius of the object squared. That's the universal formula that they're all going to follow. But that coefficient, you don't always know it, and the problem should give it to you. So yeah. Energy. The only thing new in energy is now you have rotational kinetic energy. It's 1/2 I omega squared. By now you should be noticing that I is like the same thing as mass except for circles, and omega is V except for circles. So if you ever forget these formulas, you can think back to the transitional, and then if you just remember, oh, I use I instead of M and omega instead of V, then you can just get these formulas back without having to remember them. So momentum. The angular momentum is represented by an L, and it's the mass times the velocity of the object times by the distance from times by r again, times by sine, or PR sine. So P, remember, is the momentum, translational momentum, and then R sine. So it's a cross product of P and R again. So first problem, there's only going to be 4 this week and no FRQ. I've gotten a lot busier with classes, my summer classes. The workload is really high, so that's why this video came out a week late, and it's still very short. Hopefully the next 2 videos will be regular length and on schedule. I'm trying to get these videos out on a weekly basis, but it's not always happening. Anyway, let's get back to work. What does the radius of a curve need to be for a car traveling at 20 meters per second to pass through it safely? The coefficient of friction for rubber tires on asphalt is 0.7. So this would tell us that, okay, we need to use centripetal acceleration. We need to use the normal frictional force, because that's going to be the restoring force for the curve. And so we'd set that equal. We'd say that 0.7 times by 9.80 times by the mass, right, which we don't know, is equal to the mass times the velocity squared, which is 20 meters per second. So that 400 meters squared over second squared over r. And if we rearrange, cancel out mass on both sides, we'd say that 0.7 times by 9.80 meters per second squared, that should be squared, sorry, times by r is equal to 20 meters per second squared. And so we divide by that, and we'd say that r is equal to 58.3 meters. And so one interesting application of this is that when you're driving or watching your parents drive, and as they go through curves, the curves have different speed limits, and this is how they calculate those speed limits. So this is a car, and it's traveling at 20 meters per second, so that's 40 miles per hour. So if the radius of the curve, that coefficient of friction is the ideal coefficient of friction. If your tires are worn out, then it's going to be lower. So if the radius of this curve is smaller than that, then the speed limit has to be lower. Or if that coefficient of friction is lower, the speed that you need to be going through that curve is lower. And so that's a little interesting application of physics. If you look through and look at things around you, you're going to find a whole lot, because physics is all about understanding how the world works, and how the world works and what we can do about it. Okay, what torque is needed to accelerate a 5 kilogram hoop with radius 0.25 meters to 10 radians per second and a distance of 100 radians if the moment of inertia for a hoop is mr squared. Okay, so here the coefficient for the I is 1 over 1, so it's ignored. This is going to combine kinematics and dynamics. So what we're going to do is we're going to condense, and so since we know the net torque is equal to I alpha, then we can say that the angular acceleration alpha is equal to the torque over I, and so we can just plug that directly in and say that 10 radians per second squared is equal to omega squared is equal to 2 times by omega naught, which is 0, plus 2 times by alpha times by theta. So 10 radians per second squared is equal to 2 times by the torque T over 5 kilograms times by 0.25 meters squared times by 100 radians. And so solving for what T is, we'd say that T is 0.156 newtons times Newton meters. There you go. So moving on. 500 joules of work are done making an object accelerate to 10 radians per second from a stop. What is the moment of inertia from the object? So we'd say that 500 joules is equal to the difference in energy, or just the energy because there's no kinetic energy in the beginning. And so we'd say that 500 is equal to 1/2 times I times by 10 radians per second squared. Solving for what I is, we'd say that I is 10 kilogram meters squared. Problem 4, last problem. A 0.5 kilogram ball traveling at 10 meters per second hits the edge of a 5 kilogram door with a length of 0.25 meters. The ball bounces off at a speed of 7 meters per second in the opposite direction because it's bouncing off. What angular speed is the door traveling at? So we can say that 0.5 kilograms times by 0.25 meters times by 10 meters per second, because it's hitting at a 90-degree angle, so we can just drop the sign, is equal to 0.5 kilograms times by negative 7 meters per second times by 0.25 meters plus 5 kilograms times by 0.25 meters times by v. And so we'd say that v is 1.7 meters per second, and divided by 0.25, we'd say that it's traveling at 6.8 radians per second. So that's all the problems for this week. I really recommend, since this video is so short and there's a lot of content in it, there's a lot of stuff that you need to know about circles. Google rotational kinematics physics problems, and just go through websites and work on the problems. Sorry I couldn't make more questions this week. See you guys next week. We're doing waves and simple harmonic motion, so that should be pretty interesting.